Hello, my name is Mark, and I'd like to show you how I solve Kenken puzzles. I'm going to explain everything as if you were a beginner. However, I have chosen a hard puzzle because I need to demonstrate all the different methods that I use to solve Kenken puzzles. I'm not an expert, so cannot guarantee that I've learned every possible method, but I have done a lot of 9x9 puzzles which were described as hard and have found the methods I'll use in this video to have been sufficient. Here is the puzzle that I chose to use, a 6x6 one, and you can see what a mess it can be when you do it in the small format that you get in the newspaper. So I've copied the same one onto this much larger sheet of paper for clarity. I find that at this scale I have a much smaller chance of making a mistake. So for beginners, here's a quick rundown on the definitions and what is required to solve the puzzles. First of all, we have a 6x6 grid. Kenken can come in various different sizes, but this is probably the most common one. And it's arranged in rows, 6 rows and 6 columns. So like Sudoku, the solution is to try and put the numbers 1 to 6 into each row and each column without any repetitions. Unlike Sudoku, we have cages. And these are indicated with the dark outlines. The numbers that go into the cells of each cage need to give the result indicated at the top left-hand corner of each of those cages. So for example, here we have 6 plus. So these three numbers here have to add up to give us 6. In the case of this cage, we've got 12 times. So this number multiplied by this number multiplied by this number must give us a product of 12. So it could be 1, 2, and 6 in some order. It could be 1, 3, and 4 in some order. But it could also be 2, 2, and 3. Because the 2 and the 2 would be in different rows and different columns. And therefore that doesn't break the rule. Note that with multiplication and division, there's only ever 2 cells. Here's a 3 divided by. It would be just too tricky to try and solve it if you had more than 2 cells for that. But with multiplication and with addition, you can quite often get 2, 3, or even 4 cells in this case. So once again, we've got rows, we've got columns. We need to get 1 to 6 in each one of those. And then we also have these cages, which have a number up the top telling us what we need to get in those cages. So the first step is to look at the freebies, and there is one here which is a 2, which means that immediately we can put a 2 in there. So the next thing to do is to look at the cages that give you the minimum possible solutions. So for example, down here we have 30 multiplied, and the only numbers between 1 and 6 which can produce the product of 30 when multiplied are 5 and 6. So in this square down here, in this cage down here, we can immediately put down the possibilities of this being 5 and 6, or maybe 6 and 5. When we have enough room to write in the options, I show them as pairs across the adjoining line like I've done. I also like to put a circle around them just to indicate that it is a pair, because it means that the 5 and 6 from this particular row have to be down here, which means that in these 4 cells up here, we have 1, 2, 3, and 4. I quite often put a little line like here just to make sure I remember we're talking about a row and not a column. That's the great thing about finding pairs. As soon as you can get it down to a pair, you know that you've isolated where those numbers are. And you can cross out 5s and 6s from all the other cells in that row or that column. Here's another cage that we could start with, looking at the 6 plus. When you think about the numbers 1, 2, 3, 4, 5, and 6, the only way you can get 3 different numbers that add up to 6 is for that to be 1, 2, and 3. So I'm going to put down 1, 2, and 3 as the possible numbers here. I'm also going to just circle this one here, because it just reminds me that we've got those numbers all finalized. There's no other possibilities, and we're looking in that direction. So in this first column, we've already got 1, 2, 3s all sorted out and 5s and 6s, which means that the remaining cell needs to be the 4. We keep looking at other cells for the fewer possible solutions, and when you look down here at the 10 multiplied, 10 is the product of 1 times 2 times 5, and 2 and 5 are both prime numbers, so there's not really any other option. So I'm just going to put 1, 2, 5 down here. We've already got a 2 in this column, so I'm just going to automatically eliminate that one and just write 1, 5 and 1, 2, 5. So this is a triplet. It means that those 3 numbers must go in those 3 cells, meaning that these ones over here must be 3, 4, and 6 in some order. Another cage that just gives us a few possible options is the 3 divided by. So between 1 and 6, the only way you can get the result of 3 would be to have 2 and 6, or 6 and 2, or 1 and 3, or 3 and 1. Now that we've started putting numbers in some of the easier cages, we have some idea of what numbers cannot fit in the harder cages. This means less writing and less crossing out of numbers. Again, a tidier Kenken means less mistakes. It's very annoying to get halfway through a puzzle and then spot that you got, for example, 2 5s in the same row, and going back to spot the error is often futile. Making too many errors will often result in people just giving up on Kenken puzzles, and that would be kind of sad because Kenken really does exercise a unique part of your brain, I believe. And one thing I do when I'm learning is I actually choose Kenken puzzles that have the solution. So for example, this is a solution for this particular puzzle I'm doing at the moment. And as I work through it, I just double check to make sure I've got the numbers in the right place. So for example, that 2 was given to us. And here we have worked out 4. And I can see that I'm basically on the right track. And then I just put it to one side and keep working on it. So I've gone ahead and filled in all the small numbers, some things just to have a look at with this 4 minus box. When you look at 4 minus, the only way you can get that is 6 minus 2 or 5 minus 1. You can't have 4 minus 0. So there's really only 4 possible pairs, 1 and 5, 5 and 1, 2 and 6, or 6 and 2. So that's a nice easy one without too many numbers. When you get to some of the bigger ones, like for example 12 plus, the numbers of ways you can add up to 12 is so big it's impossible to try and put little pairs across the adjoining lines. So I just write 1 to 6 in all the different cells, and we'll try and eliminate that. Same with the 12 minus. Same with the 17 plus here, but because we've got a 4, I've written 1, 2, 3, 5, 6, and because we've got a 2 here, I've automatically taken the 2 out of that one. I've left this one because one thing that we can see immediately is that because we have 1, 2, and 5 within these cells down here, it means that this cannot be a 5, which means that we do have 2 more numbers we can solve already, and that's the 6 and that's the 5. And just to make sure I'm on track again, we'll just double check the answers, 6 and 5, so that's good. Once I get good at this, obviously you won't be looking at the answers, but while we're still learning, that's the way to go. So we've got 1, 2, and 5 covered here, and we've got 6 there, which means that this must be either 3 and 4 or 4 and 3. And that is a pair going in that direction. Just giving a bit of attention to this 12 multiplied by here. I have put in all the numbers, but just to show how I got there. If you look at 12 multiplied and you look at the prime factors, it breaks down to 1, 2, 2, and 3. Those are all prime numbers now. You can't go any smaller than that. So those numbers can be combined in various different ways. For example, 1 times 2 times 6, or 1 times 3 times 4. And this is where I have made mistakes and have ended up ripping up the puzzle because I haven't looked at this in enough detail to make sure there's not a combination that I should have thought of. And I've actually gone to the trouble of producing a list. So for example, for a 6x6 Kenken, all the different numbers that you'd have in the top left-hand corner, like 12 multiplied, I go along here to the multiplication. I see if I've got 3 cells, 1, 2, 6, 1, 3, 4, and 2, 2, 3 is another possibility. 2, 2, 3. And that's all there is. And now that I've gone back to the sheet, which I've double checked over and over again, I can feel pretty confident to move on. But the important thing to look at here is that the possible numbers we're going to have here are going to be 1, 2, 3, 4, and 6. There's actually no 5 there at all. So we need to actually eliminate the 5 from those cells because they're not going to be in the answers. And just to make sure I'm thinking down the right line, yep, there we go. The answer is going to be 1, 3, and 4. So it's this one here, although I don't know that yet. So I need to cross up the 5, cross up the 5, and cross up the 5, and I know that's not going to be one of the options there. So the method I use most frequently in order to try and find another big number to put in one of the cells is to go through each of the rows one at a time and each of the columns one at a time and try and find one unique number. To demonstrate what I mean, let's have a look at some rows to start off with. So when I look across that row, I can see that there's more than one 1 in different cells. There's more than one 2, and they're in different cells. This has got the whole lot. This has got the whole lot. So automatically, I know there's no unique numbers. Here we have, and don't forget these circled ones as well. We have a 1, 2, and 3. We have a 1, 2, and 3. We have a 4, 5, 6, and 4, 5, 6. So there's nothing I can learn from there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Automatically, there's nothing I can do in that row as well. This can be a bit tedious, but if you do the double checking of each row and each column and make sure you've crossed out all the possible numbers, you'll find that something will appear more often than not. So in this one, we've got the 4 covered. I don't have any other 4s written here because I've already eliminated them as I've written in the numbers. But I've got a 1, 2, 3, 5, and 6, 1, 2, 3, 5, and 6, and the 4, so that's all covered. Here we've got 1, 2, 3, 4, and 5, and 6. 1, 3, 4, 5, and 6, and the 2, so we've covered everything there, and I need to actually eliminate these 5s now that I've written in that 5. So this is one thing you need to keep checking on all the time, is just making sure you've eliminated all these numbers. We've got the 5 here, so we know that it can't be a 5, and because this can't be a 5, we know that can't be a 2, and that's what these pairs mean. So I can cross out both those pairs at the same time. Also, because of this 2 here, I know that can't be a 5. So the options we have now are 1 and 4, 3 and 6, and 6 and 3 within that cage. If you've been along all the rows and down all the columns and haven't found any unique numbers, then you need to look for some other possible way of eliminating numbers. And when I look at this particular cage here, I can see that they have to all add up to 17, but I've already got a 4. So I know that these 3 have to add up to 13. 13 plus 4 gives me 17. Now, if this was a 1, and that actually was the answer for that cell, then I'd have to have 12 in the other 2 to add up to 13. And that's not possible because they both have to be 6s. So from that, I know that this cannot be a 1. It's not that I cross out the 6s. I know that this can't be a 1, because if this is a 1, it would give me an impossible situation. So I can cross out that 1. And that applies the same to these ones as well. One thing I did notice when I was looking down the columns is that the only place I have a 5 is here and here, and they're both in the same cage. So because they're in the same cage, I know there's no 5, I know there's no 5 there, so I've eliminated those already for another reason. I can't do anything from that, but I can actually just maybe put a little underlining there and remind myself that the 5 must go there. Now the next thing to realize is that along the columns, along the rows and up and down the columns, you have the numbers 1 to 6, and one plus 2 plus 3 plus 4 plus 5 plus 6 is equal to 21. Because these three cells must add up to 13 and we have a 3 or a 4 down here, we can say that 13 plus 3 gives us 16 for these cells, or 17 if it's a 4. So with 16 and 17, and knowing that the sum of the whole column must be 21, we know that these two have to add up to, the difference between 21 and 16 is 5, and 17 is 4. So these have to add up to 4 or 5, and we certainly can't get that with a 6. So we know that there's no way that can be a 6. Those numbers are just too big. And once again, just double checking. If I bring this on, we'll see, yep, it's a 1 or a 4 in those squares there. So we haven't made a serious mistake, even if that logic wasn't correct. When you have a cage where you've written the numbers in 1, 2, 3, 4, 5, 6, rather than doing pairs like here, it's important to try and look to see if there's any eliminations you can do. So for example, if this was a 6, then these two would have to add up to 4. Is that possible? Anyway, 1 plus 3, 1 plus 3, it is possible. So 6 is still possible. If that's a 4, you have to have some way that these can add up to 6 to give the full total of 10. Can we get that? Yes, 1 and 5, 3 and 3. Oh, that's not possible because it's in the same column, but 4 and 2. If this is a 3, we have to be able to produce a 7 somehow, and that could be a 6 and a 1. So this 3 is still okay. If this is a 1, we have to produce a 9, the sum of these two cells, and we can get that with 4 and 5. So based on that, I know that these numbers are still all relevant, and I can't knock them out yet. Looking through all the rows and columns, there's nothing that can stands out immediately as a unique number, but looking at this particular row, you can see the only place that we have 1 is in these two cells, which are both part of this cage. So if one of these numbers was 1, then the other two would have to add up to 9. And say this is the 1, and the biggest number you can have is 6, which means this can't be a 2 and a 3. You'd have to have a 4 there. So we can eliminate that and that immediately based on the fact that we know one of these is a 1. And I'll just put a line underneath it to show that it's a 1, like I did over here with the 5s. We know one of those numbers is a 5. One more thing we can learn from this particular cage is that because this is 5 or a 6, there's no way that these numbers can be 6, because if this was the smallest of the two 5, if one of these was 6, you'd automatically be 11, which is more than you're allowed to have. So both of these numbers can be eliminated for that reason. Right, having checked all the horizontals and verticals, the rows and the columns again, and not finding the unique numbers, and checking all the individual cages and not seeing any other numbers that can be eliminated, one gets to a point where you could give up or keep looking. There may be another way we can solve it, but I'd like to take this opportunity to look at what I consider one of the last resort methods of solving Kenken, and that is trial and error, when we need to use an eraser and a pencil because we might have to remove it all and try something else. So the approach is to look at cells where there's just two options. For example, this is a 5 or a 6. This is a 3 or 4. This is a 1 or a 5. We could try any of those. So the idea is to guess a number. And so, for example, let's just go ahead and say this is 6. And what we do now is we follow through as if that was 6. And if we can't come to any conclusion, then that's unfortunate because we then have to try somewhere else. But if we can get to a place where we actually have a mistake, we have duplicate numbers on the same row or column, then we can say, right, that's not a 6, it must be a 5. And we've actually determined that definitely. So let's just follow through this. So 6s get knocked out. All the 6s along here, including this one, and all the 6s up in this direction, so they all go, which means that we know this is a 1 and a 5. This 6 goes, because this is a 1 and a 5, it means this can't be a 1. It means this can't be a 1. And also because now we said in the 12 times within this cage, we had the options of 1, 2, 6, 1, 3, 4, or 2, 2, 3. We've now got rid of the 6 altogether, which means that we know it's not the 1, 2, 6 possibility, and it's only the 1, 3, 4, or 2 and 3. So we know that the solutions for this cage is either 2, 2, 3, which would have to be like this, or else it's 1, 3, 4. But it's certainly not the 1, 2, 6. So what else can we eliminate? Down here, we've got a 6, and we know it's not a 1. Here, and we know there is a 1, so that must be the 1, which means that 6 and 1 and 3 gives us a sum of 10, which is what we need in that cage, which means we can cross off the 3s and the 1s in that row, which we've done. Up here, we can cross off the 1s, which means we've got a 6 and a 2. We can cross off this 1 here and the 2, so we know this is a 5. And I'm constantly trying to look to see if we've got any mistakes occurring yet. Can't see anything yet. So this can't be a 5, that must be a 1, which means this must be a 2. And so we can cross off the 2s and the 5s up in that cell. We can cross off the 2 there. Here 1, 2, 6, 5. We can cross off the 1, 2, 6, 5. 1, 2, 6, 5. 1, 2, 5, 6. 1, 2, 5, 6. So we've got 3 and 4 here, which is now a pair. That must add up to 7 either way, which means this must be a 5 in order to give us the total of 12, which means that with this pair here, 1 and 5, we must be 1 and 5 that way around, so we don't have the 2 5s in the same row. And just checking so far, we've got no mistakes that have occurred so far. So this 6, which was our trial, might actually be correct, but we need to press on and see what else we can find. So with that 1 there, we can cross that 1 off there. We can cross that 1 off there. This 6, we can cross off this 6 here. With this 6 here, we can cross off this 6 here, which means this must be a 4 and a 3. 1, 2, 3, 4, 5, which means this must be a 6. The only way we can get 2 minus with a 6 would be to have a 4, because we can't have an 8. And that 4 would cancel out this, which means that we have a 6 and a 3, which crosses off this 3 and 6, which means we have a 1 and a 4. And this is when we get to a conclusion of this trial, because we now have 2 4s in the same column. And assuming that we haven't made any mistakes, we've gone a long way towards solving it down that track, but we've come up with an error. There were only 2 options, which means that the correct answer here is actually 5. And now I will do a lot of erasing. So what we've just done is quite frustrating, and really it's very rare that you need to do a trial and error to solve a problem like that. But because we've actually found out a new number, we'll continue and see what we can find out. So with the 5 now, we can cross off those 2 pairs because there's no 5 there. We can cross off this 5 here, and because we know there had to be a 5 here or there, we can therefore determine that this is the 5 there. And coming along, we can cross off the 5s there, and any more 5s here, no more 5s there. I like to cross off the numbers actually, if I remember, in the cells where we've actually got a solution, because sometimes it's easy to look at those when they've actually been, the cells have been solved. Now, because this cage has to add up to 10, the only way we can do it is to have 1 and 4 down here. We can't have 1 and 3, so we know this is a pair here of 1 and 4, and we can just eliminate those so we don't get confused with them. And because we've got 1 and 4 means we can cross off this, which means that we've actually got a pair of 3 and 6 working in this direction, which means we can cross out those 3s and 6s. We can cross off that 6 and that 3. And in this direction we've got a 1 and a 4, so we can cross off that 4. Looking back at this particular cell here, if you remember, these 3 here have to add up to 13, with that add up to 17. So we've got 5, which means that we're left with 8. And the only way we can get 8 in these 2 lower cells is with a 6 and a 2. And there's only 1 2. So that has to be the 2, and that has to be the 6. So now we can, once again, eliminate more numbers. So for example, this is a 6 that goes off. Now at this point, I'm not going to drop my pen and put down the big 6 and 3, because it's really important to keep going through and cross off all the numbers. Otherwise, you're going to have to keep doing double checks and picking up on those. So looking up here, we don't have a 2 or a 6, so those 2s can go. We still haven't determined the 3 and the 4, but we know that one of those must be the 1, which means that looking at these 2 options up here of 2 2 3 and 1 3 4, we have a 1 up here, which means the solution is certainly 1 3 and 4. So these 3 numbers are 1 3 and 4, so we can cross off the 2 and the 6. And in fact, we can cross off this 1 as well, because we know this is the 1. So that's a 3 or a 4 in that top cell there. We could start looking at rows and columns again to look for unique numbers. And if you did that, you would find that looking down this particular column, you got a 4 and a 3, a 1 and a 4, 2s and 6s and 3s and 4. So this 3 and 4 are actually pairs, and they cover all of those 2 options, 3 and 4, which means that this can't be a 4, and we know it's a 1 anyway because it's the only 1 in that column. So we can go ahead and put a 1 there and a 4 there, and I'll cross off all the numbers. Now coming back to this one, we remember this was a 6 and a 3, and we'd actually finished that. So we can cross off the 6s in this row and look for any 3s and 6s here. Look for any more 2s, any more 4s. Just keep scanning up and down and across and making sure that there's nothing we've forgotten. Now this 1 and 3 has become a pair, which means the 1 and the 3s are certainly there, so that can't be a 1. And these 1s and 3s up here need to be crossed out as well. And now because we've got this cage here with quite a few crossed out, it's probably worth doing a quick check to see if any numbers just couldn't work. For example, if this is a 6, can we get a 6 by adding 2 numbers on the other one? We can't anymore. So that means this cannot be a 6 because there's no 5 and 1, there's no 2 and 4, which means this is certainly not a 6. If this was a 5, can we get a 7? 5 and 2, yes we can. If this was a 4, can we get an 8? 6 and a 2, yes we can. If this is a 3, can we get a 9? No, we can't. So it means this can't be a 3. And if this is a 1, can we get an 11? 5 and a 6, 5 and a 6, yes we can. So we've eliminated a few from this cell just by simply doing that, and we can do the same from here. If this is a 2, can we get a 10? 5 and a 5, yes we could. If this is a 5, can we get a 7? 5 and a 2, we could. If this is a 6, can we get a 6? 4 and a 2, yes we could. So that's another approach you need to take. Just to remind you, that's the approach you need to do anytime that you've got your numbers 1 to 6 written along the bottom rather than pairs written across your joining line. Because by seeing that this was a 6 and automatically crossing off the pair, you're basically doing that same function of what I've just been doing, trying to eliminate any numbers that don't make sense. Right, having checked all the rows and the columns, I can't see any unique numbers, but I do know that the only 6 in this particular column fits within this cage. So one of these numbers is a 6. So because this is 256 and this is 256, what we can do is we can just say, well, let's pretend this is a 6. What numbers would this have to be? So if this was a 6, we would have to have these two add up to 12, add up to 6 as well to get the total of 12. So that would have to be a 5 and a 1. So it could be the 1. If this was the 6, and the only other way we could get these to add up to 6 would be the 2 and the 4. This would have to be a 5 and a 1, and we don't have a 1 there. So from that alone, we can say this cannot be a 5. It didn't matter which one of these we chose because they're both identical. So we have a 1 and a 4 as the options in this cell. One cage that we haven't given much attention to, which we need to look at now in order to progress, is this top right-hand one. We've eliminated a couple numbers here, so it's worth looking to see what pairs are not possible. So for example, if this is a 5, do we have a 3 on the other side? Yes, we do. If this is a 4, do we have a 2 or a 6? Yes, we do. If this is a 2, do we have a 4? Yes, we do. If this is a 1, do we have a 3? Yes, we do. So let's look from this side now and say if this is a 1, to get a difference we'd have to have a 3. We don't have a 3, so this cannot be a 1. That would be like a pair, one of these pairs that just doesn't work. If this is a 3, we'd have to have a 1 or a 5, which is fine. If this is a 4, we'd have to have a 2 or a 6. We have a 2. If this is a 5, we'd have to have a 3, which we don't have, which means this cannot be a 5. And to finish off the cell, if this was a 6, we'd have to have a 4, which we have. So having eliminated 2 numbers there, if we look down here, we've still got some 1s, but that 5 means that this is the only one in that whole column that is a 5, which means from doing that little exercise, we've just identified another big number. So by doing that, we can cross out this 5, we can cross out this 5, and know that this is a 2. And from crossing that 2 off, we know that the final one has to be the 1 here. So I'll now cross off all the numbers that match those columns and rows. Right, having eliminated those numbers from up here, we can see that we now have some more solutions. This is 5 and this is 2. So let's cross off the 5 and the 2, which is going to give us a 4 there, the only one left. And going along with this direction, we can cross off that 5, giving us a 6, which is the only one there. Going across here with a 2, we can cross off that 2. And jump to the next number, which is the 4. At this point, we might be snowballing to the end. You never quite know. Sometimes it's just 1 or 2 more things that needs to be sorted out. So that was a 4. The next number we had was the 6 here. So cross off all the 6s down here and across there, which means we've got a 5 here.